Hello everyone, welcome to webinar on Midas Gen for seismic analysis with special emphasis on masonry pushover analysis. My name is Nivedita from Midas IT. In this webinar, we are going to talk about Midas family programs, introduction to Midas Gen. There will be seismic analysis capabilities of Midas Gen discussed. And then further we will have a look on into lateral force-based method and response spectrum method. Then we'll discuss about pushover analysis on masonry structure. There will be a demonstration on the same, and rehabilitation measures will be discussed, and lastly the time history analysis will be introduced. Midas as a company was established in 1889, and since then the program has been distributed in over more than 120 countries. There have been more than 540 number of employees and 18,000 number of clients and more than 60,000 number of users worldwide. Midas IT has 6 branches all over the world, one in China, USA, India, Japan, UAE, and Russia. There are mainly 2 business areas of Midas. One is engineering consultancy and the second is software developments. So we'll be looking at the software developments under bridges, buildings, geotechnical and mechanical fields. Let me take you to the users of Midas. These are the worldwide users. Talking about Midas family programs, firstly we'll start with the bridges. So in bridges we have Midas Civil, which is integrated solution system for bridge and civil structures. Any and all types of bridges can be modeled and analyzed. Then for the Midas FEA is advanced nonlinear and detailed analysis system. Further, in structures we have Midas Gen, which is an integrated system for buildings and general structures. So today we will be looking at Midas Gen program. Then there is Midas D Shop, which is an auto drafting and rebar detailing module. It can also generate bill of materials. We have Midas Design Plus, which is a structural component design and detailing program. Under the geotechnical, we have GTS NX, which is a 3D finite element based geotechnical system, and there is SolveWorks, which is a 2D finite element as well as analytical geotechnical solution. Under the mechanical, there is Midas NFX and Midas FX Plus. Now let's talk about Midas Gen, which is a one-stop solution for buildings and general structures. These are some applications of Midas Gen program. Under the buildings, there is Burj Khalifa, Gangsa Twin Towers, so such kind of high-rise structures can be easily modeled and analyzed in Midas Gen. And other than that, we have got plant structures, so blast furnace, phoenix, and dust catchers and scrubbers. So these such kind of plant structures can be created, and modeled and analyzed. Some spatial structures like Beijing Olympic Stadium, FIFA World Cup stadiums, Beijing airports, Incheon airports, so such can be easily modeled with very user-friendly interface of Midas program. Then there are specialty structures. So in this is one of the example of masonry structure, and over here we have got another example for solid modeling that can be done in Midas Gen program. So these are some applications. Other than that, we can also analyze and design airports, hangars, pavilions, subway stations, transmission towers, cranes, pressure vessels, machine structures, underground structures, and so on, as this is not just a building program but also a general structure program. Coming to the seismic analysis with Midas Gen, these are the 4 seismic analysis that can be performed in Midas. In linear analysis, we have static and dynamic both, as well as for nonlinear analysis, static and dynamic are available. User-friendly program, we have got the ribbon menus, and we have got tree menus and message windows, making it very user intuitive. Now this is a model, a general building model that has been generated, and on this we can apply the earthquake loadings, static earthquake loadings in the x, y directions with positive, negative eccentricities. So over here in the workstream menu, you can see these are the load cases that were already generated. Now the tabs in Midas Gen are as per the work procedure, so you can just go from left to right, and as you can see, these are for the modeling purpose, then boundary supports, and then to the loadings, analyze the structure, check the results, and perform the design, and then check the reports. So I'll be going directly to the loads, and in the static loads, we have got the seismic loads that can be applied. I'll be going a little bit slow because of the delay in audience view. So here we have got the seismic loads now. So for lateral force method, I'll just go over here and add. We can select the load case name, that is EX positive, and this is a Eurocode 8, that 2004 code that we can use. Then further we can provide over here the site specific parameters, and then over here we have the fundamental period. This fundamental period you can manually provide, or you can simply click on this small three dotted box right over here and see that all the formulae from the code have been displayed. So these first three formulae can be can be readily used because the program can automatically find the height from the structure that has been created. And other than that, we need to provide the AC and the D values by ourselves over here for using the fourth and the fifth formula. So basically you can use any of these formulae as per your structure condition, and then you can go ahead, provide the scale factors for applying the loads to a particular direction. Like for example, for EXP, that is earthquake in X direction, can apply 1 factor for X direction and 0 for the Y. And further, we are also going to have positive eccentricity, so we can include the positive eccentricity over here. So that is it, and in Y direction anyway the scale factor is 0, so the eccentricities won't matter. Now even before performing the analysis, we can check the forces by clicking on this seismic load profile. As you can see over here, this is the story force graph. We have story shear graph and overturning moment graph as well. These are the values. You can see the story shear, base shear right over here. And the program is also capable of providing a calculation sheet. So this is how the values have been taken from the inputs that we have provided. And these are the calculated values which can be used further for your report generations. So this was about the static load in the X direction, positive X direction with positive eccentricity. So that can be applied, and also further we can apply in the negative direction by just changing this accidental eccentricity to negative. As you can see over here, we can intuitively see how the program has applied the forces at the center of the diaphragm. And the Y direction, all I have to do is change the scale factors. This is positive, EYP positive, and EYN for negative eccentricity. So as you can see in the workstream menu, we can easily understand if the loads have been applied or not. And we can also check the values displayed onto the screen. I'll change this to kilonewton meter. So this is how we can also see the values of the shear forces applied onto the structure. Okay, so that was about the lateral force-based method. Now I'll go back to the presentation. Next is the modal response spectrum analysis. So this is just a two-step procedure. We need to just provide the design spectrum and then create the load cases. And along with that, of course, we need to have the eigenvalue analysis, or to find the natural frequency of the structure, we have to perform the eigenvalues and Ritz vectors and such kind of analysis has to be performed. So the advantage over here in the program is that the Midas Gen program is capable of finding the most critical angle at which maximum phase shear can be obtained. So to see this procedure of how to apply modal response spectrum analysis, I'll go back to the program. In the program, we can perform this dynamic loads, dynamic static linear dynamic analysis. So that is response spectrum function, firstly, that we have to define. So this is the first thing. We'll click on design spectrum and we can choose Eurocode 8 and the required parameters. So we are done with defining the design spectrum. So if you have your own values, then you can just input them from here itself. So this is Excel compatible, so you can just copy and paste your values over here. After we define the response spectrum function, we can go ahead, use the design spectrum function in the load cases. So here I can create one major response spectrum load case. So now to find the major angle, that means the most critical angle, without doing any iterations, the manual iterations are not required to be done to find the most critical angle at which maximum phase shear is obtained. So this is automatically done by the program, and it can show you at which angle the program has actually applied the response spectrum loads. We can select from here the modal combination control, CQC or SRSS, and we can check on the design spectrum function to be used and click on add. So in this way, we are done with application of load cases, response spectrum load cases. And then the next part comes about the eigenvalue analysis control. So herein we have got eigenvectors as well as Ritz vectors to find the natural frequency. Now when it comes to like 30 or less than 30 number of modes, we can use the Langsos type of eigenvectors. And if there are more number of mode shapes required to attain the 90% of mass participation, minimum 90% of mass participation, then we can go for the subspace iteration. And in case where we have included some base oscillators or dampers, and where we are not getting the 90% of mass participation at really high modes as well, then we can use these Ritz vectors. So these are the available eigenvalue analysis controls. And that's it. We are done with application of the response spectrum loads in Midas Gen. The program is very intuitive. As you can see over here, we are applying the loads and it has been come over here in the works tree menu. So this tree menu is like very intuitive. At one glance we can understand what all things have been applied onto our model. Okay, now let's go back to the presentation and we shall discuss regarding the pushover analysis now. So the pushover analysis is basically based on the assumption that structures oscillate predominantly in the first mode or in less number of modes of vibration, and that is during any seismic event. In Midas Gen, after the analysis and design is performed, we can start with pushover analysis. So let us take a look into the pushover analysis for performance-based design. we'll see how these functions are there in Midas Gen program. So I'll go back to the program now. So this is the masonry structure basically we have. Over here we have the global control. In the global control we can include the geometric nonlinearity, or we can just keep it none, not include the large displacements basically. And then over here we can have either the initial load from the nonlinear static analysis with initial nodes, or we can import from any other static analysis that has been performed. Then this is about the hinge data option. We can provide these data for the stiffness reduction ratios. And these are certain convergence criterias, and you can also have the program stop performing the analysis if at all there is yielding of in shear or axial components, or if the supports are uplifting. So that's there. Then in case of point spring supports, we can choose to apply the nonlinear properties or assume the nonlinear properties to be linear when it comes to pushover analysis. Then further over here we can check with the wall nodal connectivity. So we can choose the walls, if there are walls that we're using in case of pushover analysis, then we can check its nodal connectivity if it's pinned or fixed. So that is about the pushover global control. This is the first step. The second step in pushover analysis is the load cases. So in the load cases we have, one second, we need to provide we'll use the sulfate, and we can use permanent structures, non-structural ones, these are the dead loads, and for variable load we can have 0.3 as the value. And then so after the global control has been defined, then we can go ahead with the load cases. So in the pushover load case, we can provide over here if we want to include the P delta effect or not, then how the initial loading is to be used. Is it the what type of incremental method, the load control or the displacement control method? So these methods are available over here. And then further we can even ask the program over here as well to stop the analysis in case maximum drift is there, or the drift at the center of the floor diaphragm is going beyond limits, and then drift calculations by average displacement of story. So all these things we can ask the program to stop the analysis. Then the load patterns. So we can select from here, as per Eurocodes, we can select static load cases or uniform acceleration. And other than that, for other American codes, we have this mode shape and normalized mode shape into mass that can be used to provide the program for the load patterns. So this is about the load case, and then after that the third part in applying the pushover is the hinge properties, wherein we define the hinges. Now the advantage in Midas Gen is that after the analysis and design has been performed, the reinforcement that has been obtained is used for automatic calculation of hinge data. So the properties of the hinges can be automatically calculated by the program. We do have auto calculation over here, as you can see. So this is just an example. So in this way, after defining the hinge properties, then we are good to go ahead and then after defining the hinge properties, we have to go ahead and analyze the assign the hinges to our elements, and then we have to go ahead and perform the analysis. Now in Midas Gen, this pushover tab is specially there available for easily applying the analysis onto our structure. And also we have under the task pane, the procedure basically provided, or the required steps that are to be used in case of pushover analysis are listed down right over here. So this becomes much more easier for understanding how and what we have to do exactly when it comes to pushover analysis. So these are the steps, 4 steps. Firstly, global control, then pushover load cases, defining the pushover hinges, then assigning the pushover hinge properties to the elements. Then we can perform the analysis and then further check with the post-processing results. I'll go back to the presentation. So let us discuss some more about the pushover analysis. When it comes to pushover analysis, the earthquake load is applied on modal in an incremental basis. Now, to account for the non-linearity in the member, the plastic hinges are required to be introduced in the model. So these plastic hinges these form sequentially, and as the plastic limit is reached, we can see them with step incrementation. Now with this, we can evaluate the performance characteristics through performance point. As you can see over here, the performance point is nothing but the intersection point of the capacity curve and the demand curve. Herein we can get the design displacement. So this is the maximum inelastic capacity of the structure for the given earthquake. And we have to check with the target displacement for the limit state of damage limit, or limit state of significant damage, and limit state of near collapse in case of Eurocode 8. So this is the location. In this webinar, we shall discuss more regarding the pushover analysis for performance-based design of a masonry structure. So it is really nonlinear behavior of a masonry structure, of an unreinforced masonry structure, and that is the reason why linear static analysis is inadequate and also inaccurate. There are 2 methods for predicting the nonlinear behavior. One is by using the accurate finite element meshed model, and the other is by using the equivalent frame method. So although meshed model gives accurate response and a cracking pattern, there is a requirement of high time cost, and you need a lot of computational skills, so which is not always available, or time is not always available with us. So we shall thus look into the equivalent frame model, which shows essential characteristics of perforated walls response and can evaluate the key design parameters of ultimate strength, maximum displacement, as well as failure modes. So here in the equivalent frame model, we can have division of the walls, vertical walls, as piers, and the elements lying about the perforations are the spandrels. So the equivalent frame model comprises of piers and spandrels. So in the nonlinear behavior of perforated wall, we can idealize it by using hinges and nonlinear links. So these are positioned at the center and the ends of the pier and spandrel. So these hinges represent basically shear failure and flexural failure of the piers and spandrels. Now in this webinar, we shall see the demonstration of pushover procedure on masonry structure. Here I have listed down the steps required. So first we have done that was pushover global control, then pushover load case, defining the hinge properties, assign hinge properties, then perform the pushover analysis, and then we can check with the pushover curve, and then we can go ahead check the pushover hinge status result. So I'll go back to the program now. So as you can see, I can use this task pane over here to define or to provide the steps necessary for the pushover analysis of masonry structure. This is the masonry structure, and I shall show the actual line model of this entire structure. So this is the actual line model of the entire structure. Let me also activate the entire structure. Okay, so here we have the line model of the masonry structure. It's an equivalent frame structure. The section properties that have been assigned are according to the length and breadth of the masonry walls. So as you can see over here, these are the walls and these are the spandrels. Okay, I'll just slow down a little bit. Okay, so the first thing that we are going to do is global control. This actually we have done this before in a step before. So I'll just repeat. What we did was we provided information of the initial loading that is to be applied onto the structure. So here we selected the dead loads and the live load. So the live load was reduced to 0.3, and then further we are going to be using the femur hinges for our masonry structure. Next we are going to create the load cases. So over here we have got the load case generation dialog box, wherein we can provide the number of incremental steps. We can choose to include P delta effect. Herein you can select the method of using the nonlinear analysis by using the initial loads, wherein we can check on these options for the cumulative reaction and the displacements due to the initial loads. We can use the load control method or the displacement method for incrementation. So we can either increase the loading or we can either increase the displacements. So it is better to use the displacements for a nonlinear curve. For bilinear or trilinear capacity curves, we can use the load control. And in case of femur or Eurocode hinges, we can go ahead and use the displacement control type of incremental method. Now, when it comes to displacement control, we can choose either the global translation or we can use the master nodes. Now, the disadvantage in global is that when it comes to certain elements, like we have got some cantilevers or some parapet walls which are having really high displacement, then those values will be taken over here, and those are not actually required because they will provide us with a very conservative result, which is not necessary, which will actually make make the analysis or the requirement of the analysis pretty useless. So it's better to use the master node. Now this master node, we can have this master node at the center of the diaphragm. Okay, so for having the master node at the center of the diaphragm, we can go ahead and create one. So firstly, let us see the center of the diaphragm. We can easily check the center of diaphragm from the display tool. So this is the center of the diaphragm for the top story. Now to know the location of this displacement of this diaphragm, we can go to the queries, and from the queries we can see the story mass table. So in the story mass table, we can see the center of mass, the x and the y coordinate of that node to be created, the master node. So we can just simply select these x and y coordinates, copy them, and then go to the node element tab, create the node. We can provide over here the coordinates, or we can even simply go to the tables, and from the tables we can provide over here the values. Just paste the values. So basically I had already created this node, but we can create later on as well, no problem. So here the values were provided and the height we have to provide, so that is what was to be input over here. After the node is created, I'll undisplay the diaphragm. Okay, so this node has been created at the center of the diaphragm, and now we can use this node for the definition of load cases. So I'll go to the pushover tab and define pushover load case. So I'll have one load case for the x direction displacement. We can use the initial loads like discussed earlier, and the displacement control, in which we can choose the master node. Now we can simply click over here, and as the box turns green, anytime, anywhere in MidasGen, as the box turns green, we can use the cursor from the model itself and get the information like the node number. So now the node number is over here that we just clicked on, and then further we can select the direction of the displacement to be applied, and the maximum displacement to be applied to this particular node or to the entire structure using this node is 20 mm. After this, we will just uncheck over here for stopping condition. There's as such, we know it's not going to actually have any height drifts, then we can just uncheck that. Then further we can choose the load pattern. So this is just the pattern in which the displacement is going to be applied in. So we can either choose the static load case or the uniform acceleration as per the Eurocode. So I'm choosing over here the static load case, which will be the EQX. That means the earthquake lateral force space method, earthquake applied in positive x direction. So that is what has been applied with a scale factor of 1. So this is done. Then I can just click on apply. So by clicking on apply, we are done defining one load case, and I'll create one more for the y direction. Everything will be the same, yeah, except over here the direction of displacement is dy, and the load case to be selected is EQY. We'll delete this, so just EQY, and OK. So we are done with having two load cases, one for the x and y direction. We can have several load cases according to the loads, lateral force method based loads that we have applied onto the structure. That is just for the pattern of displacement to be applied. After we are done with the load cases, then we go ahead to the hinge properties. Here we can define the pushover hinge properties. We can provide the name over here. Firstly, for the piers of our equivalent frame that we have created. And then further, as these are made up of equivalent beams columns, we can select the element type as beam column, and then from here we can choose the masonry. So masonry option is available for pushover masonry analysis. Then again we can select from here the pier type, and further we can provide the component properties. So here we are going to be, as discussed, applying the Fz for shear and My for flexure. This is a shear hinge property, and we can further check from here the property of the hinge. So this is the capacity curve of the hinge, and we can define over here our own capacity curve by providing over here the values. So these values, as you can see over here, these are the strength upon the yield strength. So we can provide over here, these are the values, so I'll keep them by default. So we can notice over here, this is the yield strength, the B point, then the C point is right over here, and the D point, this is a description for the D point, and then we have the E point. So we need to know about this B, C, so that when we are checking the hinge status, we can understand where exactly the displacement is coming at what is the hinge status beyond the yield point, or it's below the yield point. So after this is done, for the shear, we can also have a look at how the program provides the property calculations. So this is for the hinge property calculations for the existing structure, and we can also see over here the flexural resistance. So these all information is available in our online help menu. We can readily refer to it at any point of time. So I'll go ahead now and define the flexural hinge property. So in the flexural hinge property, I'll keep this as 6, and 0.9. We can intuitively see how the curve is being formed, the capacity curve. After we define the hinge properties, we need to also provide the masonry property information. This is an existing building, so the compressive strength, so this one is 2.67 for this structure, and 0.6063 Newton per mm square. So basically this compressive strength is for the mortar between the adjacent bricks, and we have the shear strength of the mortar itself, that is between the top and bottom bricks. So between two top and bottom bricks, this will be the shear strength. And over here, this is the vertical stress distribution coefficient, K. So we shall keep this as 0.85 itself and click on OK. So this was for the pier. Click on apply. Next, for the spandrels now, just select the spandrel type, and then further with the properties, if you want to modify these at all, the flexural properties as well, we can still modify that. And so on. Okay, so that is about the properties. Now masonry properties over here, that is about the mortar. So this again 2.67, and for the shear strength in the absence of vertical loads would be 0.063 again, and this is the HP value, which is 100,000 Newton. This is for flexural resistance calculation. So here we are done with the definition of the hinges. The next part is assigning the hinge properties. So over here in the worksheet menu itself, we can see these are the hinges that we had defined, and all we need to do now is to assign them. So for that purpose, for the piers, I can select all the vertical line elements. To select all the vertical line elements at once, we can just simply change this selection filter by direction to only Z direction, so that when we say select all, then only the vertical elements are getting selected. And then just by drag and drop, the hinge property has been assigned. These are for the walls. Now for the spandrels, I can change this selection filter to XY, so that if I'm making selections, only the spandrels or the horizontal elements are getting selected. So in this way, these are the spandrels that we have selected. And then just simply drag and drop to assign the spandrel hinge properties. And we can see over here, this is how the properties have been assigned to all the elements. So these are the steps that we are done performing. And now the last thing that we need to do is perform the analysis. So as I had made some changes in creating the nodes, I'll firstly perform linear analysis. Okay, so in a very short period of time, the analysis is complete. And then I'll perform the pushover analysis. So again, in 0.45 seconds, the pushover analysis has been performed. And now we can go ahead and check the results. So that is the important results that we need to check is the hinge status result and the pushover curve. So I'll be showing the hinge status result over here. We can select over here the load case name, and we can see the status of yielding. And also we can check over here, as we have provided Fz and My as a property of hinges. We can check the result for dz, that is displacement in z direction. That's what a program can provide. And we can see the legend. We can also see the deformation of the structure. So for step 1, no hinges have been formed, the plastic limit has not been reached. So we can further go on increasing, sorry, this is for the status of yielding. Yeah, sorry. Yes, so this is the status for FEMA yielding because we had applied FEMA hinges. So the step 1, there is no yielding. We have linear behavior of the hinges, and then further we can just go on increasing the steps. And as you can see, the light blue color of hinges, so I'll just take to the hidden view. So these are the locations of the spandrels. So basically we can see that the spandrels are going beyond the linear limit. It's in the plastic zone. The B and C that we had seen earlier in the capacity curve that had been defined. And we can just go on increasing the steps and check if any further yielding has been taking place in the piers. So as you can see, the yielding is forming in the spandrels only. That is for the X direction. For the Y direction also we can check. So the yielding is going on for this spandrels itself. So this is the result that we need to check. We can see this hinge status result in the form of tables as well. Under the beam summary result, you can check on LCX and LCY and go to the DZ table. So over here we can see the status of the hinges, if it's elastic or if it's between B and C. Then further we can even see over here the performance. This is IO, that is immediate occupancy level. So this is one result that we can see. Then further we can check the pushover curve now. And this is the curve that we have got, capacity curve of LCX. This is for LCY. This is the base shear versus the displacement graph. We can check for the target displacement. This is very important. The target displacement. And as you can see over here, the demand is very low as compared to the capacity. So the response spectrum is like going really high beyond the curves, really up. And I'll just change the graph range. Let's make it 0.20 and this is 0.3, 0.5. So this is where actually the performance points would be located, but since the demand is pretty low and the capacity is really high, we can see that right over here. So it's okay. We do not need to have any retrofitting done as such, or we do not need to design this structure for any retrofitting purposes. So in this way, we can get the results. So I'll go back now to the presentation. These are the hinge properties and hinge properties for the spandrel formulae for axial resistance, shear, and flexural resistance. Now, after we check the hinge status, and if at all the hinge status is yielding, then we can check, or we can see if the rehabilitation can be provided. So we need to then decide on what type of rehabilitation is to be done. So if the hinges are approaching the damage limit or significant damage limit, then we can decide to go either for local modification like jacketing. Then there is another method like lessening of irregularities. So if your structure is highly irregular, then you can reduce that. Then further, we can have global stiffening by bracing the shear walls. This is just an example. Then we have got mass reduction, that can be done by reducing the loads. And we can also perform seismic isolation. So isolators can be applied. And in case the hinges are near collapse, then there is no point of rehabilitation or rehabilitating the structure. The building is then required to be abandoned in that case. So that was about the rehabilitation strategies that can be performed after we know the hinge status of the structure. Using Midas Gen, we can perform the pushover analysis on masonry structures and then decide on to the rehabilitation strategies if required. Lastly, I would like to talk about the inelastic time history analysis, which is the fourth type of seismic analysis. So this can be performed in Midas Gen, and the advantage over here is that there is a huge database of earthquakes to define, of major earthquakes to define the time history functions. And you can by yourself also provide the time history functions. We can provide ground accelerations, or we can have time varying static loads. So such kind of options are available. Then here we can define the non-linearity just like we did in pushover by introducing hinges. And then the hinges can be applied to piers as shown over here for a bridge. We can also have a complete inelastic property applied to the elements. So this is about the inelastic time history analysis. In Midas Gen, we can also perform the boundary nonlinear time history analysis. So here we can perform this by modeling the base isolators and dampers. So that is a big advantage in case of time history analysis, which is there in Midas Gen. So that is it about all the functions in Midas program. I'd like to go to Midas Gen and show where our time history functions can be applied. So in the loadings, dynamic loads, over here we have got the time history analysis data, wherein we can simply provide the load cases, time history functions, and then further with any ground accelerations at all. In case of applying the isolators, so we can provide the inelastic materials right over here. Inelastic hinges can also be applied. So I'll go back to the presentation now. So this is it about all types of seismic analysis that can be performed in Midas Gen. Thank you very much for attending the webinar. If you have got any questions,